Okay, so welcome to lecture 21, I believe. Or did I skip a few? I hope I've got the right lecture. So what we're going to do today is start bifurcations in 2 dimensions. And what that is if you remember we went back to 1 dimension, we had these bifurcations where you simply had a parameter in your 1-dimensional system and you looked at how the fixed points change. And we had the example of the transcritical bifurcation, of the saddle node bifurcation where you gave birth to 2 saddles. And then we had the transcritical saddle bifurcation where the nature of the roots just changed, or the nature of the fixed points changed. And then we had the pitchfork bifurcation where you had one that came and it split into like 3, and some were stable and some were unstable. So the same game you can play in 2-dimensional systems. And in fact, the 2-dimensional systems include everything that you've had in 1-dimensional systems, but there are new things now that can form as well. So for example, all the ideas of the fixed point where you had fixed points forming and fixed points disappearing that you can have in 2-dimensional systems. The case where you have fixed points changing the nature of their roots you can also have, but then there's a whole bunch of additional things we can have as well, because you must remember now in 2-dimensional systems you have fixed points and limit cycles. And so the limit cycles, you can have fixed points becoming limit cycles, you can have limit cycles disappearing, you can have limit cycles becoming fixed points in several different ways. And so we're just going to explore all those possibilities and sort of enlarge the idea, what we have with bifurcations. Another comment is in the 1-dimensional system, we drew that bifurcation diagram, which was usually a diagram of the fixed point versus the parameter. Okay, and then you had the saddle node bifurcation where you simply had the 2 things forming, the 2 fixed points forming, the pitchfork bifurcation where it got its name. And you can do similar things in 2 dimensions, except that now it's a 3-dimensional picture, right? Usually you have the 1 parameter that you tune, and then you have the fixed points or the limit cycle, and that's usually a 2-dimensional surface embedded in a 3-dimensional surface. But I'll illustrate that more carefully. So just to get the definition straight, again, for what a bifurcation is, it's a change in topological structure of the solution as the parameter in the solution is varied. And what can happen is you can have fixed points being created, they can disappear, they can change their stability, and you can create limit cycles. They can also be destroyed and change their stability. So we have an enlarged range of possibilities, and I'm simply going to look at how you analyze them. Okay, so the first example we have, and I think if you can just hit the light, sorry, that's just above the overhead projector. I see some people are squinting. The one closest to me, I think it is. Ah, sorry, the other one. Sharp, thank you. So the first bifurcation we have is the generalization of the saddle node bifurcation. And what I've put in here is a lambda equals to 0 bifurcation. Because what you can do with bifurcations, the best way to view them in 2 dimensions is as trajectories in that diagram that we plotted. Remember we plotted the diagram of the eigenvalues of the linear system? And so if we're looking at fixed points, a very natural way to look at the fixed points is how the eigenvalues actually change. And when you have a bifurcation, you're basically going through one of those boundary value or boundary conditions in that diagram. So in other words, when you go from stable to unstable, you're changing your trace, right? So you're basically changing your trace from negative to positive. If you're going from a spiral to a center, then you're changing also the trace from negative to positive. When you're changing the actual from a saddle to a fixed point, then you're changing the determinant. Okay, so if you start thinking of bifurcations of fixed points in 2 dimensions, it's very useful to go back to that diagram and actually see how the parameter has changed the eigenvalues of your fixed point. And so with lambda equals to 0, I mean a bifurcation that takes place when one of your eigenvalues go to 0. Okay, so typically you then go through a saddle. And so the classical example that they have, once again, they call it the normal form, is this x dot equals to mu minus x squared, and y dot is equals to minus y. So this is a very nice, simple example. It completely decouples. So you look at the y dot, and it's just equals to minus y. So you basically have y equals to y0 times e to the minus t. So it is a decaying function to y equals to 0. And then this one is where all the interesting dynamics is. Okay, so you basically have a quadratic, so you potentially can have at most 2 fixed points. And then this one, all it does is make sure that you get damped onto a y equals to 0, because your solution you can just write down, and it is y equals y0 times e to the minus t. So everything eventually goes to the line y equals to 0. And so if you analyze the system, and once again, the analysis of the bifurcations is exactly the same as the analysis we've been doing, at least at the first step. You get the fixed points. Okay, so you look for where the fixed points exist. So if mu is greater than 0, you have 2 fixed points. Basically, x star, y star equals to plus minus mu, and then it's always on the y equals to 0 axis. If mu is equals to 0, then you have 1 fixed point, basically the origin. And so you can see you have the case where you have 2 fixed points going to 1 fixed point. And if mu is less than 0, then you have no fixed points, basically. And so if you remember what the saddle node bifurcation was in one dimension, this is exactly the same thing. The property that it had, you capture again. It's basically a pair of fixed points are created and or destroyed. Okay? But the analysis technique, we still go on. So let's compute the Jacobian. We work it out. It's minus 2x star, 0, 0, minus 1. It's a diagonal it's a diagonal Jacobian. So then the eigenvalues are just the diagonal values. So we see we always will have one eigenvalue that's equals to minus 1, and a second one that is equals to minus 2x star. Okay, so there are the 2 eigenvalues. And what we can now see is that this value of the square root of 0, square root of mu 0, if we substitute this back into the eigenvalue, we see that they are both negative, and therefore it's a stable node. The second eigenvalue, if mu is greater than 0, is minus mu 0. Okay, so minus 2 times minus mu is simply positive. So then lambda 1 becomes positive, lambda 2 is negative, and you're unstable. Okay, so you have one stable node, one node that basically acts like a saddle. And therefore, you basically have the creation of this pair of nodes at mu equals to 0. You have only one fixed point and none for mu less than 0. And so we call this type of bifurcation, once again, the saddle node bifurcation. We say it occurs at the bifurcation point, which is mu equals to 0 in the parameter space. And so if we actually wanted to now draw the plot, the situation you have, or the 3 possible situations we have from our analysis is, if mu is positive, then the positive fixed point is stable. It's a stable node, so there it is. You can see the y-axis basically decaying, the y value basically decaying exponentially to the x-axis. So you can see that. You can see your eigendirections are just 0, 1, 0, 1, and 1, 0, sorry, minus 1, 0, 1, 0. Okay. So over here with a negative node, where the negative fixed point where you have minus the square root of mu 0, you can see here you have the stable eigendirection in y, which has the eigenvalue minus 1. But then here along the x-axis, you now have the unstable eigendirection So it moves away from the saddle along the x-axis. Okay, so there you have an unstable node. And so you can see that this is almost exactly the same. If you were to recall the one-dimensional systems, remember there you were to just plot the line. You know, it was restricted to moving just on the x-axis. And if you look at this line, it's exactly your one-dimensional system. The only thing that y does is have this exponential decay to the axis. Okay, if mu equals to 0, you have to be slightly more careful with the analysis because you no longer have a linear system, so you don't work out the eigenvalues. But what you have is something that looks like a semi-stable fixed point, right? Because there you can just draw in the arrows. You have x decreasing to here, it gets 0, but then it continues to decrease. You still have the exponential decay to the axes, and so this thing is basically the marginally stable or the quadratic fixed point that you get at the bifurcation. Okay, and once again, the semi-stable fixed point looks exactly like the one-dimensional problem you had in the saddle node bifurcation. And finally, you get a new thing. It starts ghosting. So what happens when mu is positive? Sorry, mu is negative, right? When mu is negative, you have no fixed points. But you still have the fact, you sort of have the ghost of a fixed point, because what in practice happens is the flow comes in, it keeps going to negative infinity over here, but here where the fixed point was, it gets very, very close to 0 and it slows down tremendously. And so even though you don't have a fixed point, you have a region where the fixed point used to exist, and this is new for the sort of two-dimensional system. The fixed point used to exist over here, and you still feel the impact of its existence on the flow that takes place. So it'll look, if you integrate the system, it'll look as if it's going to a fixed point, but the fixed point actually doesn't exist. It'll just go really, really slowly in this ghost region before it goes to minus infinity. Okay, so that's sort of a new phenomena where you still feel the effect of the fixed point once it's gone. Okay, so this is the normal form of a saddle node bifurcation. What we're going to do now is look at the general form. We're going to see what a general saddle node bifurcation looks like before we go on to actually a different type of bifurcation. So the general form of a saddle node bifurcation can basically be any two fixed points that coalesce and disappear, or any two fixed points that spontaneously disappear. And if you remember when we drew those drawings in the one-dimensional diagram, I said whenever you want to find the zeros and you have like a hump and a line. Remember we did that, and the line you move, it doesn't even have to be a straight line. And the moment where that line becomes tangent to the hump, you can have a saddle node bifurcation. The same thing is true over here. And the hump and the line that you had in the one-dimensional examples, you replace with null lines. Okay. So basically, the general features of your saddle node bifurcation are the fixed points disappear for a parameter value, say mu greater than 0, but you still, so this is still the ghost. You still see the effect of the flow, it's just summarizing the ghost. And we see the fixed point. So that's one of the properties of saddle node bifurcations. They also call this thing a bottleneck region, where the flow gets really, really slow. Okay, and then before the sort of trajectories hover there before they get released. And what I'm going to do now is go to the general case, right? So if we have a general two-dimensional system with a parameter mu in it, so we can write it this way, and it's x dot equals to f of x, y, and mu, y dot equals to g of x, y, and mu. And the way we check whether we have a saddle node bifurcation is we plot the null lines. So everywhere where f is 0 as a function of x, y, and mu, and g is 0 as a function of x, y, and mu is where our null lines are. So let's, for example, plot x dot equals to 0. And y dot equals to 0. And so for a fixed mu, a function of x, y equals to 0 is simply a line. And there we have it. So say, for example, x dot equals to 0 along that line over there, y dot equals to 0 along this line over there. So those are your null lines. If you have the situation that as you change the parameter, this, say, for example, x dot moves backwards and forth, you can see the fixed points, which are where the two lines intersect, are going to disappear. And so whenever you get a general problem like this, plot the null lines first. If you have something that's doing this, you're most likely going to have a saddle node bifurcation as you change the parameter. You'd have to check by actually changing it and plotting the null lines for different parameters, but it's most likely that it's going to happen. And so just from the null lines, you can actually plot the phase diagram. So look at this. Where x dot is equals to 0, your motion is either up or down. So suppose it's down over here. As you cross the fixed point, typically it'll change direction, it'll go up. As you cross the fixed point again, it'll change direction and it'll go down. Okay? The y dot equals to 0. Here we go. Y dot isn't changed. The only direction is the x direction. So suppose it is negative here below the fixed point. You cross the fixed point, it becomes positive over there. Okay, so it flows into the loop. You cross the next fixed point, and it becomes negative. Okay, and then typically what you would do is plot some other arrows in the regions in between, but from what you already know about the null lines, you can guess what these arrows are going to look like. So because both this one and that one point towards the left, these arrows are going to point towards the left as well. And because this one points up, it's going to be directed slightly upwards. Because remember, in these regions, they cannot change between vertical and horizontal. Those changes only take place on the null lines where x dot or y dot equals to 0, and you've already plotted all of them. So over here, the arrows point that way. Over here, the arrow has to have a component that's down and to the left, so it points down. And over here, the arrow has to have a direction that is to the right and down. So there we go, and the same over there. So you can actually, just from the null lines and being careful when you actually put in the vertical and horizontal arrows on the null lines, you can see what the flow is going to do. Okay, and the way you once again identify it is if you have the situation where you have a loop of the null lines, and you can see that by changing the parameter, the loop's going to move so that the null lines no longer intersect. Okay, so just the comments. Fixed points are at the intersection of null lines. If the picture looks like a loop over a line that moves as mu changes, then what you're going to have is that the saddle node bifurcation takes place at mu equals to mu critical, okay, and that is when the curves are tangent. So if you actually want to calculate mu critical, what you would do is you would set f equals to g, and you would set the gradient of f equals to the gradient of g, right? Because that's when the two curves are tangent. And so you would get basically one equation where f is equals to g, possibly another two where the gradients are equal, or one or maybe two when the gradients are equal. And from those equations, you can work out what mu c is. Okay. Another way of checking, and this is something I actually do, is when one of the eigenvalues are 0. So remember in the previous example, we had one eigenvalue dependent on the parameter. So, and the bifurcation took place when one of them went through 0, and that is true of this example of 2. Okay, so there's two ways of actually calculating mu c. The first thing I would do is I would calculate the eigenvalues of the fixed points, and I'd start getting suspicious when the eigenvalues go to 0, because that's most likely where the bifurcation occurs and your fixed point changes its nature. And then you can check also that at that point where the eigenvalue goes to 0, you're going to have the two lines. You're going to find the parameter, and you're going to find that the two lines are tangent to each other. Okay. So what happens there then, these fixed points collide. So for example, you're moving this line outwards, these two move towards each other, and just as in the very simple example on the previous page, we showed that when they reach that point, so when the loop is pulled, the y dot equals to 0 loop is pulled completely to the right, you're going to have that this line is, or this curve is tangent to that one, and that's when your bifurcation point is going to take place. So there are three basic checks, and they should all be consistent, right? Your eigenvalues go to 0, the line becomes tangent to the loop, and the fixed points collide, and in different situations, different ones of these are easier to calculate. So know all three of them. Okay. And once the curves separate, in other words, when this curve is free of the other one, you're going to have this slow ghost flow that occurs where the fixed point used to be. It's almost as if it feels that the fixed point was there, but it's not quite there anymore. Okay. But it can still get through, it just sort of hovers around there longer than you expected from normal. So, any questions before we go on to another one? Yes?
What happens if one of the null lines, if we move it in a particular way, then it's not tangent to the thing? How can I put it? It's tangent, but for more than one point. Like curves touch each other.
You want to draw it?
Yes.
You have one very tiny piece of chalk. So there it's tangent, right?
But at more than one point.
Oh, but then it's not yet tangent.
Oh.
Right, so if you have this progression, right? So suppose you have the loop over there, and then you have your null climb. So here's the saddle, here's the fixed point, and you'll change your parameter, right? That the loop moves up until you have basically that, right? So the fixed points are getting closer to each other, and finally you're going to have just before they go, they're still not tangent, so you sort of still have that and that, but ultimately you're going to move epsilon, and you're going to have that the thing touches at only one point. Right, so you're going to have that, and finally you're going to have that. Okay, so it will always be tangent. The only thing that you can do that it is weird is that if it's tangent, the value of the two curves at the point and the derivative is 0. The only thing, and it always has to happen, right? As you move the curve out, there's always going to be a last point where it lets go, and that's your tangent point. The only thing that can happen where the last case, in other words, with the eigenvalue, but I think the eigenvalue will still go through 0. The weird thing that can happen is if it's not just tangent, but quadratically tangent. In other words, if you have that it's not just a line on a plane, but when they leave, you have the plane and the curve having the same gradient. So that's a special case, but it's still going to be the same type of bifurcation. It's just going to be a higher order version, and your ghost is going to be stronger. In other words, it's going to be close to 0 for much, much longer because your two curves have basically had the same curvature when they departed. Okay. But good question. It's good whenever you do this to build your insights straight away. So, well done. Right, so that does saddle node bifurcations. The other bifurcation, which is the transcritical one, is very, very similar. Okay, so I'm not actually going to do it. It's very similar to the one-dimensional one. The normal form is once again the transcritical normal form for x with the y equals to minus y, there it decays onto the axes. What is interesting is when we start having limit cycles forming. Okay. So, and the case when we have limit cycles forming is something we call the Hopf bifurcation. Okay, and the truth is we've actually already had a Hopf bifurcation and we just didn't name it that way. In fact, I had a problem set that I gave you and I had to delete out all the references to the Hopf bifurcation. A Hopf bifurcation occurs when you have an unstable spiral, a stable spiral going to an unstable spiral. And what happens then is you actually have the chance of going to a limit cycle. So remember when we did the glycolysis cycle, we did the Poincaré-Bendixson theorem where we had the box, we made the box and we showed all the trajectories went inside. And in the middle there was this fixed point. And I said you could only apply the theorem if the fixed point was unstable and all the flow would be outward around the fixed point. So that type of bifurcation is what we're going to see now. So that one where the fixed point goes unstable and then suddenly you go to the limit cycle is what we're going to look at now. So there are basically two kinds of bifurcations. And remember I said the other one is a lambda equals to 0 bifurcation where the nature of the eigenvalues changed because the trace changed and therefore both of the eigenvalues were real and one went through 0. This is an example where you cross that line of tau equals to 0, not on the real line but on the imaginary axis. And so just to write that down, basically we have, suppose we start with a stable fixed point with two eigenvalues, lambda 1 and lambda 2, and we have that both their real values are less than 0. Okay, so that's true for any stable fixed point. And then you have two possibilities. Okay, the one is you can have basically a node. Okay, so how I'm going to depict the two possibilities is I'm going to take the eigenvalue, I'm going to plot its imaginary part and its real part. So I'm going to plot its motion in the complex plane. And if I have an ordinary stable node, I have two real eigenvalues. Okay, one's bigger than the other one. We approach the axes along the slowest eigenvalue. But here they are. And what happens in the bifurcation is that one of them, typically the one that's closest to 0, moves across and the real part becomes positive and the thing becomes a saddle. Okay? And this bifurcation we call a saddle node bifurcation. It also is what happens when you have a transcritical bifurcation, where you're changing the nature or the real value of one of the eigenvalues through the origin, right? They remain real. Another example where it happens that we'll look at in a little while is a pitchfork bifurcation, right? Remember the pitchfork where we had 0 and then 0 split up and it went to the sort of the square root and you had an unstable one. That is also where your eigenvalue of your fixed point moves through the origin. Okay. The second possibility is if, for example, you have a stable spiral, right? Remember the stable spiral at complex conjugate eigenvalues. Okay, so you had your two eigenvalues over there, lambda 1 and lambda 2. And what can happen is they can remain complex conjugates of each other. So basically the imaginary part is the negative of the other one. But they can both move at the same time across the the stability line where tau is equals to 0. So they can both move across that thing at the same time, and this gives you a different type of bifurcation, and it gives you the bifurcation that we saw in the glycolysis cycle. So that's the thing that they call the Hopf bifurcation. Okay, so what identifies a Hopf bifurcation is that tau is 0 and delta, the determinant, is positive. Okay, and this thing is important. Over in this example, you always have your determinant is negative, right? because one of your eigenvalues are going through 0, and the product of your two eigenvalues is always the determinant. Okay, so this case where you're the complex conjugate values, your determinant is positive, and it actually plays a really important role in the frequency of what happens. Okay. So there we go, they cross simultaneously. And so this type, the second type, where you're crossing not through the origin but over the imaginary axes, is an oscillatory instability, just like we saw in the glycolysis cycle. So it's completely new in the realm of two-dimensional systems. It's not one we've seen before. And an example is, they call it, you once again have supercritical and subcritical Hopf bifurcations in their normal forms, and they are related to the Pitchfork bifurcation, because what happens is you have a Pitchfork bifurcation in one part of the normal form, and once again you have a nice one which is a supercritical case, which you try and build nuclear reactors and aircraft wings on, so that it works well, where you have a smooth transition from stable to oscillating. Then you have a subcritical case that we'll look at next time that's totally disastrous. Okay, experimentally it's highly explosive, it's very dangerous if ever you have a system. And we're actually going to look at a number of, a sort of a video of what it does in aircrafts. Okay, so the major cause of aircraft deaths in the First World War was basically due to a subcritical Hopf bifurcation. Okay, very mathematical, but when they analyzed what was going wrong with aircrafts, they were literally shaking themselves out of the sky. And it's quite scary. I'll show you the videos. It's kind of amazing. But all of that was a subcritical Hopf bifurcation. So what I'm going to do now is do the tame version, which is actually very, very useful. It's basically how the glycolysis cycle starts. It's how a whole bunch of other cycles start in nature. And you see it in several places. So we'll do the tame one today, and I'll show you the disastrous one the next time. So the subcritical case, what you have is you have a stable spiral, and it transforms to basically an unstable spiral surrounded by a small limit cycle. And one thing I should add, which doesn't get emphasized enough, is that this small stable limit cycle has a frequency, and that frequency you can actually estimate it from the frequency you get from the imaginary part of the eigenvalues. Okay, so remember, if you have imaginary eigenvalues, you can write them as tau plus I omega. Okay, so these limit cycles are born with a frequency with an I omega of the limit of the original fixed point. So you get something of the nature of the spiral going into the limit cycle. Okay, so an example is, suppose you were to have a differential equation and you would write it in polar coordinates, and you were to get something that looks like r dot equals to AR minus r to the 3. Okay, so this thing, just if you were to, so that's still decoupled, fortunately, in polar coordinates, and you were to have theta dot equals to omega plus br squared. Okay, so I've made it up. In fact, many people have studied it, and this is the normal thing that you can always write locally that a Hopf bifurcation starts looking like this, a supercritical one. If you wanted it in xy coordinates, you would just use x equals to r cos theta and y equals to r sine theta, and you would transfer it back. Okay, so you can. It's not that it's just in polar coordinates. It can be written in any coordinate system. It's just easier to illustrate what happens in polar coordinates. And so what happens is, if you look at this R equation, it's the exact equation, in fact, that we saw in a supercritical Pitchfork bifurcation, except that now it is in the amplitude of R, right? So R, remember, stands for the square root of x squared plus y squared, so it's the radial distance or the radial amplitude of your motion in your xy plane. This theta dot is basically the frequency of the oscillator. And here we can see that it depends on omega, which is going to be related to the fixed point. But it's also dependent on the amplitude. So this is actually typical of nonlinear systems, and that's actually why I wanted the one example of the Duffing oscillator I gave you in the homework, is typically your nonlinear oscillators, they have a fixed frequency, and then it's dependent on the radius of how far you are from zero. Okay, so this is basically depends on the amplitude. And what we want to do now is we want to analyze the system, bearing in mind that these are polar coordinates and that the pictures you're going to draw are going to be in the xy plane. Okay, so the first thing is fixed points, right? The fixed points you get from this thing, it's just a radius. If r star is equals to 0, you obviously have a fixed point. And if r and in the fixed point, you can get its stability, or for the radial coordinates, simply by doing the analysis or simply by looking at the picture. So at r equals to 0, if a is less than 0, right, then it's a stable fixed point, because you basically have minus something times r, subtracting a much smaller number. So basically the dominant thing basically goes like e to the at. Okay, so it decays to 0 if a is less than 0. If a is greater than 0, you have an unstable fixed point. And if a is equals to 0, you basically have, linear analysis will give you that you have a indeterminate case. But if you look, if a is equals to 0, then this thing becomes important, and you still have a very weakly stable fixed point. Okay. But the Hopf bifurcation, it's also the bifurcation point because it's where the stability changes. So what I want to do now, so then one more thing. If a is greater than 0, you also have a second fixed point if r dot is equals to 0 that's distinct from 0. And that second fixed point is when r equals to the square root of a, right? You basically factor out this radius over there, and you find that at r is equal to the square root of a, you have a second fixed point, okay? And that fixed point corresponds to a circular limit cycle because you're basically choosing a preferred radius. And so let's just draw the three situations before we actually do the bifurcation diagram. So if a is less than 0, you're going to have this situation. You're going to basically have a spiral that decays with e to the at, right? So you have your stable spiral. If a is greater than 0, right, you're going to have an unstable fixed point. In other words, it's going to spiral away from 0. But what you're then going to have is this limit cycle where r dot again is 0 at r equals to the square root of a, right? So there's our limit cycle. And then you're going to have, for big R, it's actually going to spiral towards the limit cycle. Okay, and all of this comes from the fact that this is what determines your radius's evolution, and your angular evolution just is basically going around positively with an increasing frequency as R increases. Okay, and now if A is equals to 0, right, so put A equals to 0 there, you've basically got to, in the radial case, you've got to solve R dot equals to minus R to the 3, which you can do, and then you have what I call a weak spiral because it's no longer an exponential decay, it just decays very, very, very slowly, but it is still going to go to 0. So it's a weak spiral, and you have slow decay. And so the last thing I want to do just sort of to end this thing, is let's just look at the supercritical case. Okay, so there's our coordinates. There we have the limit cycle, which is stable. And the limit cycle has this feature that it grows continuously with A. Okay, so when you go through 0, and your fixed point goes unstable, then as A increases, so does the limit cycle. And so if you're actually going to plot a bifurcation diagram, but just in the radius, what you're going to get is basically, sorry, it jumped faster than I wanted. You're going to get your stable fixed point there for A less than 0. Then the 0 fixed point goes unstable for A greater than 0. Okay, so it's unstable. This is the unstable fixed point over there. This is your stable fixed point over there. And then your second branch, your bifurcation takes place over there at A equals to 0. And there, once the bifurcation takes place, you can form this new limit cycle, the one branch of the pitchfork, where R star is equals to the square root of A. And that's the radius of your limit cycle. And here you can see this is the radius of your limit cycle that's growing. Okay, so this is a two-dimensional bifurcation diagram where you've plotted the radius of your limit cycle as a function of A. You can only do that if you have radially symmetric equations. In general, what it's going to look like is you're going to plot a full 3D picture where this A is basically the parameter that goes along this way, and you're going to plot the phase diagram for various values of A. So here you can see A is negative, so you have your stable spiral going into the fixed point. It's going to remain that all the way to where you have A equals to 0, and you have your weakly stable spiral spiraling in algebraically to your fixed point. And at A equals to 0, your bifurcation is born, and you basically now have your limit cycle, which is getting, the radius is scaling like the square root of A, getting bigger and bigger. Anything inside this like cone is going to spiral onto the cone. Anything outside the cone is also going to spiral onto the cone, and the cone's radius is determined by the square root of A. Okay, that is typical what happens in any Hopf bifurcation. And we've already seen an example. The glycolysis cycle was just not cylindrical, or was not symmetric, so you couldn't write it in nice coordinates, but that's basically the bifurcation that took place there. And you can actually check that the frequency at which that oscillation was being born was omega, or the unstable, or the frequency associated with a fixed point that went unstable. Thank you very much. I'll see you on Wednesday, and then it'll be a fun class because I'll start looking at all the disasters that people have had. Work through the problem set. I'll talk a little bit about the Duffing oscillator from perturbation theory then as well. So it'll be good if we actually start with that one and just try and get the potential energy out. Autographs. Oh, you have a quick question. Ask it.
What's the difference between a fixed point and a circular limit cycle with infinitesimal radius?
Nothing. That's how it's born.
So there's no difference.
There's no difference. That's exactly the transition that's happening in the Hopf bifurcation. Right. So it's exactly, because I mean, if you were to look at how we wrote it in radial coordinates, right, over here, the fixed point at r equals to 0, it's at the origin. Okay. So it means r is equals to 0, and your x-coordinate is 0 times cos theta, 0 times sine theta. Okay, but theta is still spinning around. So you effectively have your little limit cycle doing its little deed with a very, very small radius. And then as it gets bigger and bigger and it gets born, the frequency stays there, and you can just see it. So the answer is nothing. It's mathematically equivalent. It's the limiting case where the two are the same.